Okay, good. Okay, let's go ahead and get started. Last class, I discussed some general features of renormalization and how we describe scattering processes in quantum field theory in terms of renormalized couplings as opposed to physical couplings. And what I wanted to do today was just to do a very explicit and relatively simple example of this procedure, just so that you can see how it works. So in particular, what I wanted to study was phi cubed theory. And I wanted to study phi cubed theory at the one loop level so that you can explicitly see how it is that the various physical conditions that we impose on scattering amplitudes allows us to fix these coupling constants, these additional renormalization constants that appear in the action, order by order in perturbation theory. So here, this is just as we started discussing yesterday, is the Lagrangian of phi cubed theory, including all of the possible counterterms. There are 4 of them. And these counterterms are used to enforce physical conditions. So for example, this counterterm y here, so this is adjusted to cancel the tadpole diagrams. So this is to cancel tadpoles. And to enforce the condition that the vacuum expectation value of the scalar field is equal to 0. Z sub g is the coupling constant renormalization, and it's adjusted order by order in perturbation theory to set g to be some physical value of the coupling. So to define the coupling, the renormalized or physical value of the coupling to be, for example, the 3-point function or the 2-to-1 scattering amplitude at some particular fiducial value of the energy. And finally, z sub phi and z sub m are known as the wave function renormalization and mass renormalization, respectively. And z sub phi is adjusted order by order in perturbation theory to normalize the one-particle states appropriately. So as you rescale phi by some factor changing z sub phi, then you would change the norm of the one-particle states, and we adjust z sub phi to set that norm equal to 1. And z sub m is adjusted so that the parameter m that appears in the Lagrangian is actually related to the physical mass of the one-particle excited states in the theory. So that's to set the mass squareds of the one-particle states to be equal to m squared. Okay. So we have 4 conditions, 4 physical conditions that we're imposing for these 4 unknowns. And all we need to do is enforce those conditions order by order in perturbation theory. So for example, at tree level, so at order g to the 0, when we turn off that coupling, z sub phi is just equal to 1, and so is zm and zg, and y is equal to 0. And at order g, rather than order g to the 0, these various terms will be non-zero, and in fact, if you work in terms of the Bayer couplings, the parameters appearing in the Lagrangian, as opposed to the physical renormalized couplings, these various renormalization constants, z sub phi, zm, zg, and y, will all actually be divergent. And they're divergent to cancel the naive divergences that will appear in perturbation theory. And so let's just work this out explicitly. So very explicitly, let's consider, for example, the 2-point function. So the scalar field 1-point function is set to 0 by adjusting y to cancel the tadpole diagrams. So the first non-trivial case will be the two-point function. So in free quantum field theory, the two-point function is easy enough to evaluate. It's given by the Feynman propagator if you consider the time-ordered two-point function. And what we're interested in considering is not the Feynman propagator, but the full propagator. That is to say, the two-point function in the interacting theory where G is non-zero. Okay. So here I've written it for you in position space, but of course, as usual, it's more convenient to work in momentum space. So we usually write this in terms of the Fourier transformed propagator, delta, which by Lorentz invariance is a function only of k squared rather than k. And, of course, at leading order in the coupling, this propagator will just be given by its value in free quantum field theory, namely 1 over k squared minus m squared, plus various corrections that are of order the coupling G and higher. Now, if you remember early on in this course, when we tried to define interacting quantum field theory a little bit more systematically, we introduced the notion of the spectral representation of the two-point function. And the way that that worked is that we imagined computing this two-point function, delta in momentum space, by inserting a complete basis of states right here between phi of x and phi of y. So when you have the vacuum state inserted between phi of x and phi of y, that gives you 0 because we've set the one-point function of the scalar field to be equal to 0. When you insert the one-particle states in between phi of x and phi of y there, you get just this free value of the propagator. And then in an interacting quantum field theory, you'll get corrections to this formula that I've written down coming from two-particle and higher states that will appear when you insert a complete basis of states in the representation of the propagator. And that was where the spectral representation of the two-point function came in. So two-particle and higher, so a two-particle state must have mass squared bigger or equal to 4m squared. So we get an integral over all possible intermediate states, two-particle states and higher, that runs from s going from 4m squared up to infinity times the value of the propagator for a state of mass squared s times some function rho of s that was referred to as the spectral density. And one of the complaints that I had last semester when I introduced this formalism is that you didn't have an idea for what the spectral density actually was. And now we're going to actually compute it in this explicit example. So we'll go ahead and compute this spectral density rather explicitly in phi cubed theory. Okay. Now, in order to proceed, let me first think a little bit more carefully about what it is we need to impose when we impose our physical normalization conditions. So remember that our physical conditions were that, first of all, the one-point function of phi had to vanish. That set this coefficient y. But then we set the wave function and the mass renormalization constants by demanding that the overlap of the one-particle states were normalized appropriately, okay, so that this overlap was equal to e to the I kx with the normalization constant 1, and moreover, that the physical states all had k squared equals to m squared. So how can we rephrase those two conditions in terms of this expression for the propagator that I've written here? Well, remember that this expression right here, the leading term in the propagator, just came by inserting the one particle states here in the two-point function. So if you think about it, you'll see that the condition that the one particle states are appropriately normalized and have mass m is completely equivalent to the statement that delta, the propagator in momentum space, has a pole at k squared equal to m squared with residue 1. So the location of the pole in the propagator is the mass of the one particle state, and the residue of the pole is the normalization of the field operator. And these two conditions will fix z sub m and z sub phi. So now it's just a reasonably straightforward exercise to go ahead and start computing this two-point function using Feynman diagrams and use this physical condition to fix these renormalization constants. And so what I'd like to do now is go ahead and do that explicitly. And along the way, we'll meet a lot of new sort of mathematical tricks and techniques that are going to be very useful for us when we calculate more complicated loop diagrams. Before I continue, let me pause and see if there are any questions. Any questions? Is this more or less clear? Is this less clear or more clear? More clear? Less clear? Somewhat clear? Okay, let's go ahead and do the calculation, and then if there are questions, feel free to stop me and interrupt.
So is
yes.
The first condition, that gives you unitarity?
Sorry, the first condition,
that,
well, the first condition is really, you mean the condition that delta of k squared has a pole at k squared equals m squared?
well,
That's really the definition of what we mean by mass. That's the statement
that's
that,
on shell.
yeah, well, that's this, like, you know, for example, the parameter m that appears in the Lagrangian a priori has nothing to do with the mass of the particle. It's equal to the mass of the particle in free field theory. Once you include interactions, it may or may not be equal to the mass of the, in general, it wouldn't be equal to the physical mass of the first excited state. And so z sub m is introduced so that order by order in perturbation theory, you rescale that term in the Lagrangian so that the thing that you call m is actually the physical mass of the particle. Likewise, in free field theory, phi is an operator. So in free field theory,
But
yeah.
to come back to what you just said,
Sure.
well, it doesn't saying physical particles propagate on shell, doesn't that guarantee causality? So
Sure. I mean, this has nothing to do with causality per se. This is really the definition of what we mean by m. How is the parameter m related to the mass of the states in the theory? Is m equal to the mass? Is it equal to twice the mass? Is it equal to 4 times the mass? So, in free field theory, if I set z sub phi and z sub m equals to 1, then m would be the mass of the excitation. Once you include interactions, all bets are off. Likewise, this factor of 1/2, why did we introduce that factor of 1/2? We introduced that factor of 1/2 because in free field theory, that factor of 1/2 meant that the one particle states were all appropriately normalized, so that their inner product was just of k with k prime was a delta function rather than 12 times a delta function. Now, once you include interactions, it's no longer guaranteed that you'll get a delta function instead of 12 times a delta function. And that's what that factor z sub phi is doing there. What we're going to do is we're going to continually adjust z sub phi as we work in perturbation theory in order to enforce the condition that the one particle states are normalized appropriately. That's sort of an important point. In the same way that last class, when we looked in phi-4 theory, and we talked about, I think it was phi-4 theory, we talked about the coupling constant renormalization, and we saw that really, when we talk, the parameter that appears in the action as a coupling constant doesn't necessarily have anything to do with a physical thing that you observe. And so you need to rewrite everything in terms of physical things we observe.
But you're calling these physical conditions, and
Yes.
to me, the things that really matter are utility and causality.
Okay. But, I mean,
Well, I
those,
guess I
of
get
course, unitarity and causality are physical conditions. But let's put it this way. The parameter m that appears in the Lagrangian, how do you know what that is, right? You need to decide what it is, okay? And the choice that we make is that m is the mass of the first excited state. Because that's something we can measure. You don't actually measure parameters in the Lagrangian. You measure physical quantities. You don't ever measure, so in the case of the coupling constant normalization we discussed yesterday, the lambda phi to the 4 coupling, you don't actually measure lambda. What you measure is a 2 to 2 scattering amplitude. Okay? And you use that to define what you mean by lambda. And in particular, Tuesday, we decided to define lambda to be the value of the 2 to 2 scattering amplitude at a particular scale. So likewise, I'm defining m here to be the mass of the first excited state. And what I'm realizing is that in an interacting field theory, there's no guarantee that that means that the appropriate term in the Lagrangian is 1/2 m squared phi squared. It could be 1/2 m squared phi squared times something else. Okay? And that something else is what we're going to compute. This is kind of like the important, sort of, one of the important issues of renormalization, that the parameters that appear in the Lagrangian a priori have nothing to do with physical observables. Okay. Other questions? Yeah. Good. I mean, really, really the physical conditions that I'm imposing are the definition of what I mean by the mass and the definition of what I mean by the field operator phi. I'm declaring that phi creates a one particle state which is normalized, which is appropriate, which is unit normalized. Okay? And I'm declaring that it creates a one particle state with mass m. Good. Okay. So let's go ahead and start computing this guy. So to compute delta, we just need to go ahead and expand in terms of Feynman diagrams. So delta is a two-point function. So of course, the first term will just be the free propagator. And then in phi cubed theory, the first non-trivial correction to the free result will be the one loop expression that I've written here. And then there will be various counter terms that, as last class, will just represent by an x. And then there will be higher and higher terms. And these counter terms, the ones that contribute to the two-point function, will arise from the wave function renormalization and the mass renormalization, because those both multiply terms that were quadratic in phi in the Lagrangian. Okay. Now, when we calculate delta, it actually turns out that there's a very nice way of organizing our expansion for the propagator, okay, which allows us to actually sum up an infinite number of Feynman diagrams all at once. So what I want to do is I want to define a quantity that I'll call pi, which is equal to all diagrams that contribute to delta, which will still be connected if one line in the diagram is cut. And we usually give a special name to this class of diagrams. We call them one particle irreducible. Or 1pi, simply because, well, they have the property that if you remove one of the particles, one of the lines from the Feynman diagram, you're still left with something non-trivial. And then So then in pictures, we can represent all those diagrams like that. So here I've just inserted a blob that I'm calling pi here that represents any possible contribution to delta that has the property that it's still a connected diagram even if you cut one of the lines. Here, that's not a loop with a pi in it, that's just some general blob. Okay. And then the propagator, the full expression for the propagator, can be written as an infinite series where you first add one 1pi contribution, then two 1pi contributions, then three, then so on and so forth. Now, one statement I should make that's not entirely obvious is that in order for this to be true, I've used the fact that there are no tadpoles that contribute. So for example, you might worry about a diagram that looks like this. I don't know. Something like that. But in fact, because of the no tadpole result, because of that y counter term, all diagrams of that form will cancel. So the only diagrams that contribute to the propagator are those that come from the one particle irreducible diagrams. Is that clear? Yes. Question.
This is a general phenomenon. You never feel able to write the two-point function with a sum.
Yes. Yes. This is. I mean, we're going to have to make some modifications to this. So, for example, probably next class we'll do this in electromagnetism, and in that case, pi has some index structure. So we'll have to modify this a little bit. But in general, this is true. This is a general result. This sort of thing will hold in general. Is this clear, this fact that you can write the propagator as a sum of one particle irreducible diagrams, more or less clear? Yes?
I don't really understand. Is a free propagator or one particle irreducible diagram?
No, I'm not going to include the free propagator as one
Could you
particle
give an example
irreducible.
of one particle irreducible diagram?
Okay. Let me give you an example of a one particle irreducible diagram. So that is an example of a one particle irreducible diagram. This is another example of a one particle irreducible diagram. And those are the only ones that appear at this order in the coupling. So, yeah. Question?
What about other number of point functions? For example, frequent function and important function.
Okay. Yeah, so there are similar things that one can say. In general, you know, the fact that I can sum up, you know, I'm going to, in 1 second, I'm going to use this observation to sum up an infinite series of Feynman diagrams. This kind of trick generally only works for special sorts of diagrams. Really, what's helpful here is the fact that we're considering a two-point function, and there are very few types of terms that can contribute to two-point functions. So, you know, there are other sorts of limit. There are also other kinds of circumstances in which you can sum up an infinite number of diagrams, and there's usually a physical reason why. So as we'll see in just 1 second, there's actually a very nice, because of this fact, there's a very nice physical interpretation for this quantity that I've called pi. Okay. So let's go ahead and investigate this expression for the propagator that I've written here. So this is the propagator at momentum k squared. And so let's just investigate this expansion that I've written right here. So of course, the leading term is just 1 over k squared minus m squared. Okay? I'm leaving out my factors of I epsilon for a minute just to make the formulas a little simpler. But they'll come back to haunt us in a little bit. And then what is the next term? Well, the next term has two propagators, a 1 over k squared minus m squared, a factor of pi of k squared, and a third factor of 1 over k squared minus m squared. And then this third diagram right here has a 1 over k squared minus m squared, a pi of k squared, a 1 of k squared minus m squared, another factor of pi, and a 1 over k squared minus m squared, and so on and so forth. There's a couple comments that I should make in case this formula is not clear. So one of the things that we need to keep in mind is that in Feynman diagrams, we enforce momentum conservation at each vertex, which means that each of these pi's is evaluated at the same momentum k squared, okay, because there's no other legs on to which the momentum k can go. And the other comment that I'll make is that usually when we talk about Feynman diagrams, when we're computing scattering amplitudes, you don't attach factors of the propagator for external legs. Right? However, it's important to remember that when we compute delta, we're not computing a scattering amplitude, we're computing a two-point function. And remember, the relationship between scattering amplitudes and correlation functions is that you strip off, when you compute a scattering amplitude, these factors of the propagator. So this 1 over k squared minus m squared, here and here, those are the factors that you usually strip off, when you use the LSZ formula to relate a scattering amplitude to a correlation function. And I've included them here explicitly. Okay, so we have an infinite series here, and so can anyone tell me does anyone know what the sum of that infinite series is? Yes.
The propagator over 1 minus pi over, or 1 3 propagator over 1 minus pi n to 3.
That's fair. I think, okay, that's basically right. I'm not actually sure I understood exactly what you said. But let's pretend that you were saying this. There's a minus sign. In which case you would be completely right. Okay. And if you're not convinced by this, just do the Taylor expansion, treating pi as a small quantity, because it's going to be of order the coupling. And you'll see that it precisely leads to the expansion that I wrote down above. So we see from this formula that pi actually has a very nice interpretation. Pi is essentially the contribution to the mass squared that appears when you start calculating corrections perturbatively in the coupling. So for this reason, it's usually called the self-energy of our particle. And then the statement that we impose our physical conditions, that the one particle states are normalized appropriately, and that m squared is the physical mass squared, which turned into the physical conditions that delta has a pole at k squared equals m squared of residue 1, then turn into very simple conditions on this self-energy pi. In particular, pi at m squared has to be equal to 0. Otherwise, you'll shift the location of the pole. And the first derivative of pi with respect to k squared, evaluated at m squared, has to vanish as well. Otherwise, you would shift the residue of the pole. And these two conditions can then be used to fix the wave function and mass renormalization. Is that clear? More or less? Okay. So let's just go ahead and compute this. Okay. Enough talk. Time to compute some Feynman diagrams. So pi, again, at the leading order in perturbation theory is a sum of two terms. So there's the one loop term coming from two interaction vertices, and there are the counter terms coming from z phi and zm. plus other terms that are higher order in the coupling G. So let's just go ahead and write these down. So the first term, so this is our usual Feynman diagram. So here K is the incoming momentum, and you get a 1/2 from the symmetry factor, and the coupling squared, so G squared, because we have two interaction vertices. And there's one undetermined momentum, which I can take to be the momentum P propagating on the lower half of this one loop diagram. The momentum on the upper half, P minus K, is fixed by momentum conservation. So we're left with a one loop integral, d4p over 2 pi to the 4th. And we have two propagators. So we have the propagator on top, which is a piece P. So let's rewrite that a little more carefully. So that's I over P minus K squared minus M squared plus I epsilon. And then we have the propagator from the lower vertex, on the lower half of that loop diagram, which is a P squared minus M squared plus I epsilon. And then we have the two contributions coming from the renormalization terms. So what were those renormalization terms? Let me just remind you. So they're coming from this term right here and this term right here, both of which are quadratic in phi. So z sub phi multiplies two derivatives acting on phi. So that will lead to a contribution that I'll call A. So that's A is z sub phi minus 1 times k squared, 2 powers of the momentum, because we have those two derivatives here. And then we had another one coming from the mass renormalization that I'll call B, that just multiplies m squared, no powers of k. So A here is z sub phi minus 1, and B here is zm minus 1. Good. Any questions on this? And as last class when we studied coupling constant or normalization, we're treating A and B in this equation as order G squared, so that they'll cancel, so that they can combine with these terms that I've written down here in order to enforce our physical conditions. And so in principle, that's it. Everything appearing on this slide is everything you need to know. I've written down a formula for pi, and I've written down the physical conditions that we impose, namely that pi and its first derivative vanish when k squared is equal to m squared. All I'm going to do now is introduce some calculational techniques that we use in order to simplify and understand this expression. But before I do so, let me pause and see if there are any questions. Great. Okay. So the first thing that we need to note when we look at this integral is that this integral is logarithmically divergent. The reason, of course, being that at very high momentum p much larger than k squared, the denominator goes like 1 over p to the 4th, and we have an integral of d4p in the numerator, so it's like the integral dx over x, which grows logarithmically at large x. And so one of the things that we're going to encounter is the fact that these a and b terms will need to be divergent as well in order to take care of that logarithmic divergence. Okay. Now, integrals of this sort, where you have two denominators or more than two denominators multiplying one another, arise all the time when you study Feynman diagrams. And so to simplify denominators like this, there is a very useful trick that we're going to introduce, which I believe is called Feynman's trick. I don't think it has any fancier name. It might be called Feynman's denominator formula. I'm not actually sure. And the formula says that if you have, well, it's just a very simple formula that one can easily prove to oneself. But you're going to prove it to us on the next problem set. Essentially what you do is you introduce an auxiliary parameter x that's integrated from 0 to 1. And then you integrate x from 0 to 1 of this particular combination of a and b in the denominator. And that it's a sort of pretty trivial exercise to calculate this integral and see that it gives what I said it gives. Oh, here a and b are not the same as this a and b up here. Sorry. I should have called them something else. Should I call them a1 and a2 or something like that? Maybe I'll call them a1 and a2. And then there are similar expressions involving more than one denominator. So in your problem set, you'll prove actually the general version of this statement where you have n terms in a denominator, and you write it as an integral over n minus 1 variables, all of which sum up to 1. But we're just going to need to use this simple version of the denominator formula to combine two denominators. And so the integral that we're considering, so we have an integral d4p, we have a 1 over p squared minus m squared, and a 1 over p minus k squared minus m squared. So we can write that as an integral dx, an integral d4p, and then in the denominator here, so really the utility of this formula is that it allows you to combine the two denominators together. So the denominator here, let's see, just setting a1 equals to p squared minus m squared, and a2 to p minus k, quantity squared minus m squared. What do you get? You get p squared minus m squared plus, well, a2 minus a1 will be k squared minus 2p dot k times x, all to the minus 2 power. So we've combined those two denominators together at the price of this auxiliary parameter, introducing this auxiliary parameter x. And then we can complete the squares in order to write this as p minus xk quantity squared minus m squared plus k squared x times 1 minus x. All I've done there is complete the squares to write this as p minus xk squared plus something. And then, because we have an integral d4p, we can just shift the integration variable from p to p minus xk to get rid of this factor right here. So this then is the integral dx times the integral d4p, where p is now a shifted momentum variable of 1 over p squared minus m squared plus k squared x times 1 minus x, all quantity squared. So this is a trick that we will be using again and again in this class. So whenever you encounter an integral of this type, you first use the denominator formula to combine the denominators, and then you complete the squares and shift the integration variable to write it as an integral of this type. Okay, an integral d4p of 1 over p squared plus something. Okay. Any questions on this? And very often when we compute loop diagrams of this sort, we're going to be left with integrals like this. So we're going to be computing all the time integrals that are of the form integral d4p of 1 over p squared minus something to some power. So in general, we're going to need to compute an integral of the form, what should I call it? Let's call it I, which is the integral d4p, 1 over p squared minus delta plus I epsilon to some power. So here we have the second power, but in general we might need other powers as well. So here, let's just focus on the case where n equals 2, in this case. And here delta is m squared minus k squared x 1 minus x. Okay. Now, the trick that I'm going to use to evaluate this integral is actually a rather subtle trick. And this is the first time where these I epsilons that we're introducing are going to be important. So remember in this expression, when I write this p squared in the denominator, p squared is really the sum of p0 squared minus p vector squared. So we have the time-like part of p and the space-like part of p, which appear with different signs in p squared. And so that means that this integral has poles. One pole when p0 is equal to the square root of p vector squared plus delta, and another pole where p0 is equal to minus the square root of p vector squared plus delta. So when you do that p0 integral, you need to be worried about these poles. These are the same poles that appeared when we studied the free propagator. And in that case, we had to be sort of careful about the I epsilon prescription. And indeed, in this case, these I epsilons are going to come and save us once again. Because in fact, those I epsilons just shift the location of the poles to be slightly off the real p0 axis. So if you think about the p0 integral as a contour integral, so as a contour integral, in the complex p0 plane, we start by doing an integral along the real p0 axis, and we have poles here and here, just above and just below the real p0 axis. And so that means that we can rotate the contour from the real p0 axis to the imaginary p0 axis without running into any of the poles, and thus without changing the answer for the integral. So we can rotate, and this is usually known as a Wick rotation, so that we integrate the p0 variable along the imaginary p0 axis. So what does this mean in practice? Well, in practice, this means that we can just make the change of variables where instead of working with p0, we work with IP0, which is a new variable that's often referred to as the Euclidean momentum, P naught Euclidean. So this Wick rotation is also sometimes called the Euclidean continuation of these loop integrals. Now, why is it called the Euclidean continuation? Well, the reason why it's called that is that if you look at our original expression for the form momentum squared, that's p0 squared minus p vector squared. And then in terms of this new variable, it's minus p0 Euclidean squared plus p vector squared, which means that this Euclidean momentum, p0 Euclidean, is on completely the same footing as the spatial momentum in p vector. So sometimes people just refer to this as minus p Euclidean squared, okay? Where p Euclidean is now the 4 vector whose components are I, p0, and p vector. And this is called Euclidean because whereas the p0 squared minus p vector squared is the characteristic feature of a Lorentzian spacetime, where space and time have different signatures, p0 Euclidean squared plus p squared is the signature of a Euclidean space. So that's the Pythagorean, that's Pythagoras, right? The distance, you know, a squared plus b squared equals c squared. So people sometimes get sort of worked up about Euclidean time and t going to it, and does this mean time is imaginary and all of this stuff. And those are things that I suppose are worth getting worked up over to some extent. But at this point, as far as what we're doing right now for the computation of loop integrals, all we're doing is computing this integral by cleverly manipulating contours. Okay. We've just noticed that the location of the poles is such that we can just cleverly rotate our contours in this way and turn this into an integral then that's much easier to do. So the integral that we're then doing, so we started out, let me just remind you, with this integral here, where p was a Lorentzian momentum, and we get a factor of I out front. That comes from the Jacobian when you make the change of variables, p0 to I, p0 Euclidean. And then we have 1 over p Euclidean squared plus delta squared. And now this is a perfectly, I don't want to say perfectly convergent, because it's not. It's a much easier integral to study because p Euclidean squared is a purely positive definite quantity. And so you can see that this is now an integral of something that's purely positive, that's something purely positive definite in the denominator. So no more I epsilons are necessary. So we've removed the dangerous pole where the denominator could vanish. Okay. Any questions on this? I mean, this is very similar to the manipulations that we did when we studied propagators in free quantum field theory, so hopefully it's not too unfamiliar. Okay. So, just to summarize, what we have is our expression for the free energy in phi cubed theory, which is given by this integral plus a times k squared and b times m squared. There are some factors of I and some factors of m squared floating in there. I'm just going to neglect those because at the end of the day we're just going to adjust a and b to impose our physical condition that pi in its first derivative vanish at m squared. So I can always absorb those constants in those i's and stuff like that into a and b. Okay. And I here is given by that integral that I wrote down above, where delta, okay, sorry, it's not quite given by the integral I wrote above. Okay, let me call it something else. Let's call it, I don't know, what's a good name for an integral? Okay. Yeah, I have to do the x integral. I don't know, let's call it I tilde, okay, where I tilde is the integral dx times the integral d for p 1 over p Euclidean squared plus delta squared, where delta is k squared x times 1 minus x minus m squared. Good. Questions so far? Okay. Now, and as we saw, A and B are chosen so that pi and its first derivative vanish at k squared equals m squared. Okay. So the first thing that we should notice when we study this integral is that it's still divergent. Okay. This integral is still logarithmically divergent because you have an integral d4p over p to the fourth. So how can we adjust this? So we need to find some way of doing this integral in a way that allows us to set those counter terms that will cancel this divergence. And I suppose there are really 4 different methods that there's a lot of different methods that one can use to regulate this integral. Today I'm going to talk about 4 of them. Well, I'll probably only talk about 3. The 4th I'll get to tomorrow. So the simplest way to do this and to deal with the divergent integral is to do the following. And this is probably the most physical way of thinking about it. So I is a divergent integral. Well, okay. So the simplest way to do it is to imagine that you're computing pi order by order in an expansion in k squared around the point where k squared equals m squared. And then, pi and its first derivative at m squared vanish. And so what we really need to think about then is the second derivative of pi with respect to k squared. So the second derivative of pi with respect to k squared is found just by taking the second derivative of this formula here. So a and b won't contribute. They'll vanish when you take 2 derivatives. And so you just get the second derivative of I with respect to k squared. And the important point is that when you do that, so let's just work it out, every time you take a derivative with respect to k squared, you increase the power of this denominator here, okay? Because delta has a k squared in it, so when you take a derivative with respect to k squared, you increase the powers in the denominator. You take 2 derivatives, what you'll get an x squared times 1 minus x squared times an integral d4 p Euclidean of 1 over p Euclidean plus delta, which was k squared x times 1 minus x minus m squared, now to the 4th power. And with a power of 6, okay, coming from those 2 derivatives. And so this is a perfectly convergent integral. Okay, we could work it out, we could write it down. It's just some function of k squared. Okay. So this is perfectly convergent. And so given this convergent answer for the second derivative of pi, we can then determine pi of k squared by integrating this twice. With respect to k squared, and imposing our physical conditions in order to fix the constants of integration that appear when you perform those two integrals. And so this will give you a completely unambiguous and finite answer for the self-energy pi. And one thing that's sort of cute about this approach is that it never required us to compute A and B explicitly. All we did was use the physical conditions on pi, when k squared equals m squared, and then determine pi by integrating a convergent integral. When all else fails, this is kind of the most physical, fundamental way of regularizing an integral. You take a derivative, if you have some divergent expression, you take enough derivatives to make it convergent, and then you integrate it back up, imposing physical conditions along the way to fix the constants of integration that appear when you do that integral. So this is one way of regulating that integral. And this is probably the most conceptually straightforward way of doing the integral. You know, if you're ever really confused, you could always use this method. But it actually is technically a bit more complicated than necessary. And the reason is that the intermediate steps involve somewhat more complicated integrals. Okay. In particular, every time we take a derivative with respect to k squared, we bring out those extra powers of x and 1 minus x. And so the intermediate steps in this calculation are actually rather complicated. And so we're always looking for a, whenever you have to do a computation like this, you always want to try and find a procedure where, in order to do the intermediate steps of the calculation, you're not introducing unnecessary complications. And so this is a conceptually straightforward way of regulating the integral, but one which is just technically a little complicated. Yes?
Is there any theory that this
Yeah.
works in
I mean, this theory is one where it works perfectly. It's not so hard. This is not so hard to calculate. I mean, at the end of the day, in this theory, these x integrals are a little tricky to deal with, so we're not going to really spend too much time focusing on this answer. But you could certainly do it in this theory. There's nothing, at this point, there's no reason why I couldn't assign this to you as a homework problem, computing that integral and integrating it. At the end of the day, phi cubed theory is not necessarily the theory that we're going to focus on, so I'm not so obsessed with actually computing the precise analytic answer in this case, more with just introducing the techniques. Good. Okay. One other method that we could use to regulate our integral would be just to introduce a cutoff in the integral. So this is sometimes referred to as the hard cutoff method. What does that mean? Well, it means that when we integrate d4p 1 over p squared plus delta quantity squared, instead of integrating over all values of p Euclidean, we integrate only over those values where the absolute value of p Euclidean is less than some cutoff lambda. And then this will give you an answer an answer for I which depends on the value of this cutoff lambda. But the dependence on lambda will vanish when we fix A and B using our physical condition. And this is the method that we used last class when we studied phi-4 theory. Okay, we introduced a hard cutoff in that integral, and we saw that naively at one loop we had cutoff dependence on this new parameter lambda. But once you imposed your physical condition, that cutoff dependence disappeared. Okay. So again, this is a perfectly fine procedure to use, but it also has the problem that at intermediate steps in the calculation, it introduces some complications. So this is usually complicated because the cutoff lambda breaks Lorentz invariance. Because we're introducing some new energy scale, and we're only integrating over modes with energy below that scale. So usually if you have a symmetry in a problem, then you don't want to break that symmetry at intermediate stages in a calculation. The final answer that we get for pi has to be Lorentz invariant. So that means that we should look for a way of computing pi which preserves that Lorentz invariance at all of the intermediate steps of the calculation. So a third method that one could use, and that's the method that I think I'll use to do the calculation today, is known. So any questions on this before I continue? So these two methods that I've just introduced, the derivative method and the hard cutoff, both have the advantage that they're very sort of physically easy to understand, because it's very natural to cut off an integral this way. But they both have these two problems, that they introduce sort of complexities at intermediate stages of the calculation. So instead, a much nicer approach, although not the nicest approach, is known as Pauli-Villar's regularization. And Pauli-Villar's regularization rests on the following observation. So I want you to remember when we derived the Feynman rules for fermions, the curious fact, which I said was going to be important, that fermions contribute to loops in the Feynman diagram expansions with an extra minus sign. That means that whenever you have a loop contribution to a Feynman diagram, if it's a fermion in a loop as opposed to a boson, you add an extra minus sign. This came from the statistics of the particle and the way that you had to interchange various terms in order to write that loop diagram. Okay, so what does this mean? So if we have a scalar loop of mass, where you have a scalar of some mass m, say, propagating in a loop, just add a fermionic scalar of some other mass, let's call it lambda, which would be much bigger than the mass of our original particle, which will cancel the divergence at high energies. Now, this additional fermionic scalar that we're adding is not a physical particle. Because as we saw last time, scalars have to be physical scalars have to be bosons, and fermions have to have odd spin rather than even spin. And so this scalar is really not it's not a physical particle. It's just a mathematical trick that we use in order to keep track of the divergences in the theory. We actually have a special name that we give to particles with wrong statistics that we add in order to keep track of divergences or for other reasons. We call them ghosts. We're actually not going to be using Pauli-Villars regulations so much in the calculation of Feynman diagrams, at least in QED. But when we come back to consider non-abelian gauge theories, we will encounter ghosts of a different sort. So fictitious terms that you need to add to your Feynman rules describing unphysical particles with the wrong sort of statistics that will help us keep track of various terms that appear in the Feynman diagram expansion. But it's important to keep in mind that this unphysical particle is really just a mathematical trick. Okay? It's not, there's no physical excitation. So as we saw last semester, if you have a boson with the wrong statistics, you get into all sorts of trouble with unitarity and Lorentz invariance and so forth. So really, I mean, this new particle is just included as a bit of a trick. The point being that you view lambda as being very, very large, so that the mass of this particle is so high that it's completely unobservable. And you just essentially use this additional mass parameter lambda as a regulator for your integrals, just as you did in the hard cutoff method. The only difference being that now this prescription preserves Lorentz invariance. So in this regularization scheme, all of the answers that you get at intermediate steps will preserve your symmetries, preserve Lorentz invariance. Yes?
So I thought spin statistics is a consequence of relativity. Why did introducing a fermionic scalar preserve the next one?
Okay. Yeah. I mean, when the proof of spin statistics from relativity involved, considering asymptotic states and things like that, and we're not allowing ghosts as asymptotic states. We're not allowing, we're only including. This is really more of a bookkeeping device. Let's put it this way: if you compute a Feynman diagram with a particle of the wrong statistics, the answer is still Lorentz invariant. The problems with Lorentz invariance only arise when you consider more global issues involving asymptotic states. Sorry if that's not an ideal answer, but that is actually the truth. Yeah. I mean, you could just, so for example, okay. In the present case, we have an integral d4p over 2 pi to the 4th, times 1 over p squared minus delta quantity squared. And in this regularization scheme, you just replace this with an integral d4p over 2 pi to the 4th times our original term, 1 over p squared minus delta squared. And then we subtract off an analogous computation where you have a new particle with some mass lambda. So lambda here is just some parameter that we're adding in order to regulate the integral. And you can immediately see that this is going to make the integral finite, as long as lambda is finite. Why? Well, the problem was that this term here went like 1 over p to the 4th at large p. But At p much bigger than lambda, this guy also goes like 1 over p to the 4th. So in fact, when you cancel those two terms, the leading behavior at large p goes like 1 over p to the 6th. So you get an integral d4p over p to the 6th, which is convergent at large p. And indeed, you can actually just go ahead and compute this guy. And at very large lambda, what do you get? Well, you get a factor of I that came from that Euclidean continuation. So this is just a straightforward integral. So I'm not going to bother. So you could compute it yourself. It's just a straightforward integral. You get a factor of I, a factor of 16 pi squared. And you get a log of delta over lambda squared. Again, that log has to be there because the original integral is logarithmically divergent when you take this cutoff away. So maybe I'll just make one comment about this regularization scheme. Okay. So this is the regularization scheme that I'll use today, okay, when I complete our computation of this self-energy. But in general, this is not the preferred regularization scheme for more complicated calculations. So for more complicated calculations, we usually use a different scheme known as dimensional regularization, which is something that we'll discuss probably next class. And the reason why dimensional regularization is preferred to the Pauli-Villars regularization scheme is that if you consider a theory with many different loops that you're studying, in principle, in Pauli-Villars, you have to introduce a different ghost for each kind of loop that you're considering. And these ghosts all have different cutoff parameters lambda, which have to be related to one another in some way. That's not a priori obvious. Whereas in the other regularization scheme that we'll be studying next week, it's much more clear. There's a sort of universal procedure for regulating all of these integrals at once with only one new parameter appearing rather than many. But there's a question, maybe? Okay. Was there a question?
Is it the power of
Yeah, yeah. Thank you. Good. Thank you. Good. Okay. So let's go ahead and complete our calculation of the scalar self-energy in phi cubed theory. So our expression, so let me just remind you. So this was our expression right here for pi. We had to do that complicated integral. And then we had to add those a and b terms. So pi, well, let's see, you get a minus g squared over 16 pi squared, but there was a factor of 1/2 coming from the symmetry factor, so you get a 32 pi squared. And then we have that x integral from 0 to 1 dx. And then we just regulate using Pauli-Villars. And so we get log delta over lambda squared, which was m squared minus k squared x times 1 minus x over lambda squared. And then we have these two other terms coming from the wave function and the mass renormalization. And now all we need to do is determine A and B by imposing our physical condition. So, for example, So let's just calculate, say, pi of m squared using this formula. So pi of m squared is minus g squared over 32 pi squared times the integral dx log of m squared times 1 minus x times 1 minus x over lambda squared plus a m squared plus b. So this vanishes, which fixes a m squared plus b. And pi prime evaluated at m squared is that same minus g squared over 32 pi squared integral dx. You now take the derivative of the logarithm. When you do that, that lambda squared dependence drops out. So this expression is actually finite. Remember, when you take a derivative of pi, you make the integral more convergent. So something that's logarithmically divergent, when you take one derivative, becomes convergent. So you get a convergent integral. So you can just stare at it and write it down. What do you get? You get x times 1 minus x over m squared 1 minus x times 1 minus x. And then plus a has to be equal to 0. So you actually see when we perform this regularization procedure, and when we perform this renormalization, that a is actually finite. It's given by this integral that I've written down here. Now that x integral you can actually do, so all of the x integrals you can actually do here. I haven't bothered to write down the answer because it's just some function that's not particularly illuminating. But the point is that the x integrals can be done. Okay. So a is this finite number. It depends only on the coupling constant g. Well, so it's of order g squared. So it's some number that I really should have put this in Mathematica and done it, but I actually didn't. Okay. It's some number times g squared over m squared. Okay. The interesting term is b. Okay. So you set b by setting pi at m squared equal to 0. And b is going to be logarithmically divergent. But that log divergence is designed precisely to cancel the log divergence in pi. So, for example, when you include that b term, you get a result for pi which has that minus g squared over 32 pi squared times the integral from 0 to 1 dx times the log of m squared minus k squared x times 1 minus x over m squared minus m squared x times 1 minus x. That's just enforcing the condition that pi of m squared equals 0 to determine b, and plugging in the answer for b. And then from a, we get a constant term. Or sorry, plus times x, plus a times k squared plus a constant. So the actual functional form of the answer here is not particularly important. So we could do those x integrals if you like and fix all of those constants. What I really want to do, however, is just emphasize that in this procedure, although naively we had a divergence, once we rewrite everything in terms of physically observable quantities like the mass, and then impose this regularization procedure, we get a perfectly finite quantity at the end of the day. So this procedure by which we introduce counter terms, and then systematically determine the counter terms order by order in perturbation theory, is actually generally guaranteed to remove all of the divergences in your Feynman diagram calculations. So that's something that we're going to see again and again over the next few weeks. So I'm more or less out of time now, but next class what we're going to do is return to this calculation in quantum electrodynamics and calculate the self-energy of the photon. So that'll be mathematically a sort of similar procedure. It'll be a little bit more complicated, but quite similar. And then we'll see what sort of physical results we can conclude from that. So for example, this will give us the one-loop correction to the Coulomb potential in quantum electrodynamics. So it'll give us the quantum correction to the Coulomb potential in quantum due to the interaction of photons with electrons. Maybe I should see if there are any questions before we end. Is this more or less clear? Good. Okay, see you next week.